In this section I'm going to talk about the pump characteristics. Okay, so this shows a typical graph of the pump characteristics, and so it's plotted on the axis here. You can see that there's pressure rise from the pump on the y-axis and volumetric flow rate on the x-axis, and the green line here shows the pump characteristics. So it will always follow this curve, so it can't deviate away from this. So this is for a fixed speed. I'll show you in a minute what happens when you change speed, but at this given speed it needs to stay on this curve. So it can only, for example, produce this pressure at this flow rate, or this pressure at this flow rate, for example. So you can see that these pumps can produce low volumetric flow rate at high pressures, or high volumetric flow rates at low pressures. And you can see here this is the maximum flow rate that the pump can deliver where it intersects 0, and this is the maximum pressure that it can develop where this intersects at 0 as well. So as I say, this is for a given speed. However, if you change the pump speed, or omega, the rotational speed of the shaft, then if you decrease it, then the curve has the same shape, but obviously it just kind of moves in towards the origin. So just to reiterate, these are lines, different pump speeds, and you're constrained to this curve. So you can either have low volumetric flow rates, high pressure, or high volumetric flow rates at lower pressure. So this is the characteristic curves as that showed on the previous slide, and the generic formula for this line here is written as this. So that the pump pressure is equal to some constant minus another constant times by the velocity squared, and A1 and A2, they're constants specific to the pump, so it's not necessary, you can't determine those are normally found by obviously you design the pump and then you test it and you get these curves out, and then you can fit this general equation to them. So just keep a mental note of this equation, because we'll come back to it when we find the operating point, or help find the operating point of a pump in a particular pipe network. So that shows the pump characteristic curve in terms of flow rate, but obviously what's important to pumps as well is the efficiency that they're running at. And the pump efficiency is given by this definition, so it's the power that's transferred to the flow divided by the power that's consumed by the pump. And if you remember, in a previous lecture I showed that the power to the flow can be written as the pump pressure times volumetric flow rate, all divided by the pump power. However, the pump efficiency is not constant with volumetric flow rate, as perhaps you might have expected. So it does vary, and you can see here, shown in the graph below, how the efficiency changes with volumetric flow rate for each of the different speeds as well. So you can see that there's a peak, maximum efficiency, and the maximum efficiency for each speed is a different volumetric flow rate, and that's because the way that the pumps are designed, because of that, the way the pump's designed, there's a different peak efficiency for a different combination of angular velocity and volumetric flow rate. So you can see that ideally you want to be operating around the maximum efficiency. So for a particular pump speed, you want to be working at this pressure height and this volumetric flow rate. This slide shows a pump characteristic curve for a real pump, just to show you what one looks like. So you can see, as showed on the kind of the made-up ones I showed you on the previous slides, you can see there's different curves at different speeds, and again we've got volumetric flow rate, or this is in capacity and this is in gallons per minute. And then this side we've got, instead of pressure, it's written as head. And just think back to when we're doing Bernoulli's, we can write pressure, we could write Bernoulli's either in terms of pressure, pascals, or in terms of head with the units of meters. And I said there that the two were kind of interchangeable as long as you kept the units the same. And this is an example where, pumps are an example where head is actually the preferred unit, because it makes much more sense. Say you're trying to size a pump to lift the water up to a header tank in a building. What you really want to know is how high that pump will lift the water in terms of distance, rather than knowing what pressure it is and then having to work out rho GH to find out how high it will lift. So you can see here that, if you want it to lift about 60 feet, at this flow rate, then this is the efficiency and that kind of thing. So pumps are a good example where head is the preferred unit rather than actual pressure. What's also superimposed on top of this plot is the efficiency of the pump. So you can see that its maximum efficiency, which is what I showed there, is 60 is to lift water 60 feet in the air at a volumetric flow rate of around, what's that, 9, 10, about 10.5 gallons per minute, something like that. And so this is what's called BEP, the best efficiency point. And then as you start to deviate from there, if you keep the speed constant, you can see that the efficiency drops as you move away. So this is kind of just showing a real life example of the example plots that you've seen on the previous slides.